All right, let's talk about something that can be a huge headache in neuroimaging. I mean, you go through all this work to get a brain scan, and then it comes out looking weirdly warped. Today, we're going to get into exactly what's causing this, and, way more importantly, how we can fix it. Let's jump right in. So, picture this. You spend all that time at the scanner, you've got your data, you're excited to look at it, and then you open the file, and it just looks wrong. The brain seems kind of stretched out in some spots and all squished up in others. If you've ever dealt with imaging data, you know exactly what I'm talking about.
And this right here shows you the problem perfectly. Over on the left, that's a nice, crisp T1 anatomical image. It's basically a true picture of the brain structure. But on the right, that's an echoplanar image, or EPI, the kind we use for MRI or diffusion scans. Just look where those red arrows are pointing. The whole front of the brain is stretched and distorted. That's the exact problem we're going to solve.
Now, this warping thing actually has a name, and figuring out what it is, well, that's step one. So let's get into the nitty-gritty of what's happening to our data.
The bad guy here is called susceptibility distortion. You see, epi scans, the ones for fMRI, DMRI, ASL, they're captured incredibly fast. But the price we pay for that speed is that they get really sensitive to any little changes in the magnetic field. And this becomes a huge problem where you have different kinds of tissue right next to each other, especially where your brain tissue meets up with air-filled spots, like your sinuses. That mismatch creates these magnetic field distortions that literally warp the image. It's what makes lining these scans up with our nice anatomical images a total nightmare.
Now, while all these EPI scans get hit with this distortion, they don't all suffer equally. Diffusion MRI, DMRI, is by far the worst of the bunch. Because of how it's acquired, with these long echo times, the distortions are just way more obvious. With fMRI and ASL, you still get warping for sure, but it's usually not quite as dramatic. Okay, so if we want our results to mean anything, we just can't ignore this. We absolutely have to fix it. The whole process is called susceptibility distortion correction, or SDC for short. And lucky for us, there are some really clever ways to get it done.
So we've basically got two main strategies in our toolbox for this. Up top, you're seeing examples of the Popolar method, and down on the bottom is the field map method. They look pretty different, but they're both trying to do the same thing. Measure that warp and then undo it. So let's break them both down.
First up is the Popolar method, and honestly, it's just a really elegant and clever way to solve this distortion puzzle.
I seriously love this analogy. The polar method is what we call the stretchy and squishy method. The whole idea is to grab two extra scans where the distortions are the exact opposite of each other. So in this example, the main image on the left has these stretchy eyeballs. Then we take another scan with the encoding flipped, and we get squishy eyeballs. The software can then look at both the stretchy and the squishy version and calculate what the true undistorted shape must be, somewhere right in the middle. It's brilliant.
Now, when you're out in the wild, you're going to hear a few different names for this. Popolar is one, but you'll also hear it called blip up/blip down, referencing those two opposite images. Or, if you want to be formal about it, reverse phase encoding, or RPE. It's all the same stretchy/squishy idea.
All right, so that's the stretchy and squishy way, but there's another approach that comes at the problem from a totally different angle, and that's the field map method. Yeah, so instead of taking two distorted images and trying to find the average, the field map method goes straight to the source of the problem. It uses a special scan to directly measure the problems in the magnetic field itself, the very things that cause the warping in the first place. It creates a literal map of the distortion, which the software can then use to unwarp your main image.
So which one should you use?
Well, for DMRI, with its really bad distortion, the Popolar stretchy and squishy method is pretty much the standard across the community. But for fMRI and ASL, where the distortion is a bit milder, using a field map is way more common. The key thing is just to collect the right kind of correction for the type of data you're working with.
Okay, so we get the problem and we get the solutions. But how do we actually do it? How do we tell our software, hey, use this squishy image to fix that stretchy one? Well, this is where having your data organized properly is absolutely crucial.
The answer is in the BIDS standard, which stands for the Brain Imaging Data Structure. With BIDS, you have your image files, and right next to them are these simple little text files called JSON sidecars. You can think of these JSON files as little instruction manuals for each scan, and we can actually go in and edit them to give our software specific commands for distortion correction.
And the magic instruction is this one little field right here, intended for. Inside the JSON file that belongs to your correction scan, you just add this field, and you point it to the scan you want to fix. That's the heart of the recipe. You're telling the software exactly which file this correction is meant for.
So the whole workflow really breaks down into 4 straightforward steps. First, you acquire the right correction scans when you're at the scanner. Then, you organize all your data into the bids format. After that, you just add that intended for field to the right JSON file. And finally, you run a bids-aware pipeline, which will automatically read your instructions and apply the fix for you. Simple as that.
We've just covered a lot of the technical how-to, but let's just take a step back for a second and talk about why going through all this is not just a nice thing to do, it's absolutely essential for doing good science.
When it comes right down to it, it is all about accuracy. If your brain images are warped, you have no way of knowing if the brain activity you think you're seeing is actually coming from the right part of the brain. Correcting this distortion makes sure your functional data is lined up properly with the brain's real structure. And that is just fundamental to getting results you can trust.
So let's do a real quick recap. Number 1, EPI scans get warped because of susceptibility distortion. 2, we've got 2 main ways to fix it: the p-polar or stretchy, squishy method, and field maps. 3, p-polar is the way to go for DMRI, while field maps are what you'll usually see for fMRI and ASL. And 4, the way we make it all happen is by using that intended for field in our bids JSON files.
And that really brings us to the final thought. We put so much work into designing our studies and analyzing our data, but every bit of that work depends on the quality of the images we start with. This correction step is one of the single most important things you can do to make sure that foundation is rock solid. So, the question I want to leave you with is your data as accurate as it can possibly be? Thanks for watching.